All right, welcome to the Explainer. Today, we are going to tackle a super cool physics phenomenon that you see all the time, maybe even this morning at breakfast. We're talking about the seemingly magical way that light seems to bend?
You've seen this, right? You stick a straw in a glass of water, and suddenly it looks broken. So what's going on? Is the straw actually bent? No, of course not. What you're actually seeing is this incredible illusion, and it's our doorway into understanding a really fundamental property of how light works.
All right, so here's our game plan. We'll start with that everyday illusion. Then we'll decode what's really happening. We'll look at Snell's law, that's the golden rule here, see some other cool examples in action, and then wrap it all up with a handy toolkit.
Okay, let's get into it. First things first, we're going to connect that simple trick of the eye, that bent straw, to the big scientific idea that makes it all happen.
And that scientific name is refraction. That's all it is. Refraction is just the phenomenon of light changing its direction when it travels from one transparent material or medium into another. Think air into water. Simple as that.
So let's zoom in a little bit. We're going to get a little more technical and figure out what exactly is happening right at that surface, the boundary between the air and the water. To do that, we need to meet the key players in this game. Okay, so this diagram really lays it all out for us. First, you have the light ray coming in and hitting the surface. We call that the incident ray. Then you have the ray that goes through the water and bends. That's the refracted ray. And to measure all of this, scientists draw this imaginary line. See it there? It's at a perfect 90-degree angle to the surface, and that line is called the normal. It's just a reference point, but it's super important. Now, this bending isn't just random chaos. A scientist named Snell figured out through a ton of experiments that light follows two very specific rules here. The first one's pretty straightforward. The incoming ray, the bent ray, and that normal line we just talked about, they all lie on the same flat surface, the same plane. But the second law, well, this is where the magic really happens. It turns out there is a precise mathematical link between the angle the light comes in at and the angle it bends to.
And that brings us to the mathematical heart of it all. This is the part that gives us the power to actually predict how much a ray of light is going to bend, which, when you think about it, is pretty awesome.
And here it is. This might look a little intimidating, but it's actually pretty elegant. This is Snell's law. All it's saying is that if you take the sine of the angle of incidence, that's I, and divide it by the sine of the angle of refraction, that's R, you always get the same constant number. And we call that number n21. This is the golden ticket for calculating the bend.
So what is that constant, that n21? It has a name. It's called the refractive index. The best way to think about it is like a rating. It's a number that tells you the light-bending power of a substance compared to another one. So for example, the refractive index for light going from air to water is about 1.33. Every pair of materials has its own unique refractive index. Okay, now check this out, because this is a really cool detail. The direction of the bend depends on where the light is going. So if light travels from something less optically dense, like air, into something more optically dense, like water, the ray actually bends towards our imaginary normal line. But if it's going the other way, say from the water back out into the air, it does the opposite. It bends away from the normal. It's a two-way street with different rules for each direction. Okay, theory is great, but let's actually run the numbers. Let's imagine a ray of light hitting the water from the air at a 30-degree angle. So we just plug that into Snell's law. The sine of 30 degrees, that's 0.5. We know the refractive index of water is 1.33. So now our equation is 0.5 divided by the sine of r equals 1.33. We just do a little algebra, solve for the sine of r, and we get about 0.375. Then we find the angle that gives us that sine, and boom, it's about 22 degrees. The light came in at 30 and bent to 22. The formula works perfectly.
Now, I have to stop here and make a really important point. When we say optically dense, please do not confuse that with mass density, how heavy something is. They are not the same thing. The source material gives a fantastic example, turpentine. Turpentine is less dense than water. It literally floats on top of it. But guess what? Its optical density is higher. It actually bends light more than water does. So optical density is all about light bending, not weight.
All right, so we've got the theory down. Now let's look at a couple more classic, real-world examples of refraction that you can totally spot for yourself now that you know what you're looking for.
First up is something called lateral shift. Take a look at this diagram. When a light ray hits a block of glass, it refracts, right? It bends as it goes in, but then it has to come out the other side. So it refracts a second time as it goes from the glass back into the air.
And here's the cool part. Because the sides of the glass block are parallel, the bend on the way out perfectly cancels out the bend on the way in. So what's the result? The light ray ends up traveling in the exact same direction it started in, it's just been shifted sideways. It's been laterally displaced. It's like it took a little sidestep.
Okay, example number 2, apparent depth. This one explains something you've definitely experienced if you've ever been in a swimming pool. It's why the bottom of the pool always looks closer than it really is. Just look at this diagram. You see the light rays coming from that object on the bottom? Notice how they bend as they leave the water and travel to the eye?
Here's the trick. Your brain is amazing, but it doesn't know about refraction. It just assumes that light always travels in a perfectly straight line. So when those bent rays hit your eye, your brain traces them backwards in a straight line to figure out where they came from. And that imaginary point it creates, the apparent depth, is way shallower than the real depth. Your brain literally creates an illusion for you.
All right, let's pull all of this together. We're going to create your official refraction toolkit, a quick summary of all the key ideas you need to remember.
Okay, here's the cheat sheet. Refraction, that's just the bending of light between materials. Snell's law, that's the formula that predicts the bend. Refractive index, that's the light bending power number for a material. And apparent depth, that's the cool illusion that makes things in water look closer than they are. Got it? Good.
So here's the big takeaway. Now that you know about refraction, I promise you, you are going to see it everywhere. It's in the lenses of your glasses or a camera. It's why stars appear to twinkle. It's even that wavy, shimmering air you see above a hot road in the summer. Heck, it's the fundamental principle that makes fiber optics and therefore the internet work. It's not magic, it's just amazing physics. The real question is, now that you know the secret, what other illusions are you going to spot out there in the world? Thanks for joining this explainer.